Good morning, everyone. My name is Simon Schmidt. Welcome to this webinar on the use of rehydration nutrients and fermentation nutrient additives. And we'll get straight into it, I guess. The title's fairly self-explanatory. Basically, I guess, as everyone's probably fairly familiar, there's only two major sources of nutrients for fermenting yeast, the grape, stuff that comes from the grape, and the winemaker. Nutrient levels in juice can be influenced by a whole range of conditions, including vineyard practice, harvest type, transport, processing, treatments such as SO2, disease status, and microorganism load. And as a result, the actual availability of nutrients to fermenting yeast is highly variable. Much of what I will discuss today is most relevant to fermentation of highly clarified musts and folks using active dried yeast to inoculate their ferments, but also is more generally applicable. So I guess the first step in the use of active dried yeasts is rehydration. But I want to talk about rehydration by understanding or discussing a bit more about yeast production. Propagation for the production of active dried yeast is carried out in multiple stages in nutrient-supplemented molasses medium. In the final stages of that production process, growth conditions are carbon-limited and highly aerobic. And in these conditions, the trehalose content, a disaccharide comprised of 2 glucose units of yeast, can be as high as 22% of dry weight. High levels of this sugar help to improve yeast resistance to dehydration, which we'll go into in a bit in a minute. And this is probably through its ability to replace water associated with the cell membranes. Aerobic propagation also maximizes accumulation of unsaturated lipids, general lipids such as sterols, and unsaturated fatty acids, which enhance yeast tolerance to stress during subsequent fermentation. Dried yeast, such as those pictured, are produced in a fluidized bed dryer that can reduce the moisture content to below 8%, and that becomes important in a minute as well. So the aim of this whole process is to optimize viability following rehydration. This is commonly upwards of 90%, but can be anywhere from 60 to 90%. In its fully hydrated state, a cell membrane is in what's called a liquid state, and that doesn't permit the passage of molecules into and out of the cell, except for small hydrophobic chemicals such as ethanol. Traffic across the membrane is highly regulated through a series of transporters and permeases. The membrane is composed of a variety of lipids, and in yeast the dominant lipid is a sterol called ergosterol. In this liquid state, individual molecules within the membrane are relatively free to move around. The effect of drying on cell membranes to less than 15% and down to around 8%, which is common for most active dried yeast preparations, is that the membrane goes through a transition from a liquid state to a gel state. The molecules in gel state membranes generally lack mobility compared to liquid state membranes. They're pretty much locked into position. And due to this limited mobility, gel bilayers, gel state membranes, lack an important property of liquid bilayers, and that's the ability to reseal small holes. So until the full rehydration of the membrane and return to the liquid state, the membrane can be highly permeable, and the cell potentially subject to large-scale solute loss. The aim of rehydration protocols, therefore, is to minimize this solute loss and to facilitate membrane transitions back from the gel state to liquid state. So the most common strategies used to manage viability loss during dehydration are, in the first instance, temperature. So Subarand in 2006 showed that temperature was the single most important factor in obtaining high recoveries of viable cells from dehydrated yeast. So temperatures between 35 and 43 degrees provide optimal viable yeast populations. This is consistent with all previous work and with most common rehydration instructions. And the reason this is important is because at those temperatures facilitate membrane transitions back to that liquid crystalline state from that gel state, and that helps minimise leakage during the process of rehydration. Adding salts to a rehydration medium can also help minimise that solute loss. This occurs indirectly. This can be added indirectly, or salts can be added indirectly through the use of rehydration nutrients, or more generally inactive dried yeast, as they are. This minimises solute loss through the maintenance of ionic balance. So components from inside the cell aren't going down a concentration gradient across the cell membrane. So can rehydration nutrients help fermentation progress? Although it's been shown that sterols from inactive dried yeast can be taken up during the process of rehydration, it's also the case that active dried yeast, as I said, are produced in such a way so as to maximise membrane sterol content. Therefore, it's not entirely clear what additional benefit a transfer of sterol from an active dried yeast might provide. We looked at 3 different commercially available rehydration nutrient preparations prior to fermentation of a clarified Chardonnay juice and 2 different pHs, which is shown in the graphs below in this slide. The dotted lines are fermentation curves for ferments that had been inoculated with yeast in the presence of rehydration nutrient, and in all cases the ferment curves pretty much overlaid each other. We were unable to discern any performance benefit due to the application of rehydration nutrients during active yeast preparation. I want to move on now to talking a bit about addition of nutrients during fermentation. Yeast nutrient requirements are vastly different to our own, and the yeast food pyramid, if you were to draw one like I did, looks decidedly unbalanced. Yeast can make almost everything they need, and this means that any discussion of yeast nutrient requirements revolves around components that are required in relatively small amounts relative to the amount of sugar present. After sugar, a yeast's main other nutrient requirement is nitrogen, which is usually present in quantities that permit sufficient cell growth for all available sugars to be processed. Despite being used primarily in the production of protein for growth, many other factors of concern in winemaking relate to the availability and efficiency of nitrogen utilisation. And this includes hydrogen sulfide production and fermentation performance. In the slides that follow, I want to talk about different types of nutrients, diammonium phosphate, complex and nutrient additives, which contain also amino acids and vitamins and other things. But also I want to talk a bit about oxygen as a nutrient that can be used during fermentation. These nutrients are often added either at inoculation or a third during fermentation progress, or some variation thereof. And sometimes any time there's a smell of H2S, so as a tool to reduce H2S production, I'll talk a bit about that as well. The way that nitrogen demands tie together to cellular reproduction can be seen in this data set. The left-hand graph shows biomass formation during fermentation in red, and total nitrogen utilisation, or in this case mainly amino acid utilisation, in blue. Almost all ammonia present as part of the YAN is used very quickly by yeast, and the remainder of the residual nitrogen then is all amino acid. That's the bulk of YAN anyway. And what's immediately evident is that almost all nitrogen consumption occurs during growth phase. After this, cells tend to turn amino acids over and reutilize internal components rather than require their importation. Also, in an environment with moderate nitrogen concentration, in this case the YAN was 330 mg per litre, not all the available nitrogen is used, so there is some residual nitrogen in the form of amino acids. In the graph on the right, we can see that there are both different concentrations of the different amino acids, but also there are different preferences for different amino acids. And it's on top of this residual amino acid pool that nitrogen is often added in the form of nutrient additives. So what is the nitrogen component being contributed from a standard addition of complex nutrients, for example? We looked again at 3 different common commercially available fermentation nutrient additives. Standard additions of these nutrients, throughout 30 grams per hectolitre, contributed between 30 and 50 mg per litre of nitrogen as YAN. The majority of which is in the form of ammonia. And the residual then is amino acids of various amounts. The actual amino acid compositional data I don't really have, but these amounts in general are similar to around a 200 mg per litre addition of DAP in terms of nitrogen added. Again, we tested how use of these nutrients impacted on fermentation performance in a highly clarified YAN sufficient must. We also looked at them in musts of 2 different pHs. In all cases, there was a small but significant performance benefit to the use of these nutrients, and this is most obvious for fermentation nutrient 3. So the dotted lines in this case in all the graphs were ferments treated with fermentation nutrients. The non-dotted lines were untreated, just regular ferments. For all ferments, we've seen fermentation performance improvements with the addition of these types of rehydration nutrients. But I guess it's not only fermentation performance that we're thinking about when we're adding nutrients, or in particular nitrogen, to a ferment. Grape juice nitrogen status can also have effects on wine flavour. This graphic shows the increased fermentation performance associated with increasing concentrations of initial nitrogen in the must. So in this case, we had a low YAN juice that was supplemented with DAP such that the YAN would increase to 320 or 480 mg per litre. And this work's been published by Terrea et al. In 2011. So with increasing nitrogen, we get decreasing durations of fermentation. And this is largely due to increased biomass production at these higher levels of nitrogen. However, there's a trade-off to this whole fermentation performance nitrogen scenario, and that is with increasing nitrogen comes an alteration in the flavour profile of the wine. Moving from complex characters in the slower, lower YAN musts to more fruity, ester-driven characters in a more balanced YAN must, to solvent-type descriptors in very high YAN musts, most likely driven by increased production of ethyl acetate and acetic acid in those types of heavily supplemented ferments. And this comes then, one potential benefit of using complex nitrogen sources rather than DAP for the supplementation of fermentations is that there's appears to be a reduction in the evolution of this solvent-type character in more heavily supplemented ferments. I want to move on now to talk a little bit about also of flavour management, so production of H2S. So DAP addition is commonly or routinely used to reduce growth-associated production of H2S. This graphic here shows the relationship, I guess, between initial YAN status and onset and total production of H2S. It should be noted that not all yeast respond this way to DAP addition, but most classic yeasts, as you increase the amount of nitrogen available to them, both decrease the time of you push out the onset of H2S production, so H2S production doesn't start until later, and the total amount of H2S produced is less. The mechanism by which DAP reduces H2S production is via facilitation of amino acid production. H2S is produced as an intermediate in the production of sulfur-containing amino acids. When there is sufficient nitrogen to permit their production, accumulation of H2S is inhibited, I guess, so any H2S being produced is immediately used in the production of those amino acids. But when there's insufficient nitrogen, accumulation of H2S results, and that comes out in the fermenting media. Feeding with more nitrogen again allows that H2S to be fixed again into those sulfur-containing amino acids. So high YAN DAP delays the onset of H2S production and lowers the amount of H2S produced. It should be noted that H2S can come from other sources rather than just during amino acid production, but I won't go into that in detail today, but it relates to the recycling of nutrients late in fermentation. So there is also the possibility for non-growth associated H2S production, and that type of H2S production probably isn't going to be as treatable with DAP as growth associated H2S production. I also want to touch on a little bit here, as I said earlier, oxygen as a nutrient. In the context of this presentation, more generally, oxygen can be considered as a limiting nutrient during fermentation. And that's because in anaerobic fermentation conditions, yeasts can't synthesize lipids. Membrane components then get diluted into subsequent generations in the growing population, and therefore to grow more, yeast must either produce more lipids or assimilate them from their environment. This has a downside. Yeasts can assimilate phytosterols from grape juices, but it's been shown that excessive integration of those phytosterols into the yeast membrane can be detrimental to fermentation performance. So it's probably better that that is regulated in some form. Oxygen, when added during fermentation, stimulates biomass formation through its ability to allow yeasts to manufacture, again, their own sterols, and this relieves one potential nutrient limitation. At the most basic level, oxygen can be made available to yeasts by aerobic pressing and vigorous tank transfers. Dissolved oxygen in these cases can be as high as 3 mg per litre immediately following these operations. So if musts are inoculated directly into these conditions, yeasts will compete with the chemical reactions around them for the available oxygen. In a more deliberate approaches, irrigation, sparges, venturi valves, etc. can be used to introduce oxygen directly into the fermenting must, and an aerial irrigator and open-top fermenter is pictured on the right there. As a side note, for those of you more interested in oxygen and who didn't catch Martin Day's webinar the other day, that's still available online, and his 2013 webinar, both of which are about winery scale experiments with oxygen. Now, because of this ability to stimulate sterol formation, very small amounts of oxygen added mid to late exponential growth phase is generally sufficient to stimulate dramatic improvement in fermentation performance. And again, this is via its ability to stimulate biomass formation. We looked at this capacity to stimulate fermentation, again in highly clarified Chardonnay juice with low initial oxygen. And in this work, we added air until dissolved oxygen concentration of 0.19 or 2.7 or 5.2 mg per litre was achieved. These concentrations were held for 2 hours, 48 hours post-inoculation, when the ferments were in mid-exponential growth phase, so the arrow in the growth curve just pointing there to where we treated with oxygen. And again in the fermentation curve there, so very little sugar had been used by that point. During this period, you get maximum also CO2 production, so there's little risk of oxidation. However, it can be challenging to introduce sufficient oxygen to achieve these types of dissolved oxygen concentrations due to the stripping effect of the CO2 that's being produced during fermentation. In this case, we observed, as with nitrogen, that increasing oxygen input resulted in decreasing fermentation times, but beyond about 2.7 mg per litre dissolved oxygen during fermentation, there was no improvement in fermentation performance. Is this the case with all ferments? Is it limited only to highly clarified musks? So we also evaluated the effect of oxygen addition on a high solids uninoculated ferment, a completely opposite type of thing. And in this case, the addition of oxygen did not result in any performance gains. But the oxygen treatment we found did promote non-Saccharomyces yeast growth. and their persistence right through to the end of fermentation. We also observed increases in the production of low molecular weight sulfur compounds, and this is probably aligned with the increased population of non-sap yeasts. In general, when we treat white ferments with oxygen, we do see some level of increased low molecular weight sulfur compound production, but in these wild high solids ferments, that was particularly pronounced. The increases in H2S and other sulfur compounds following oxygen treatment of some white ferments is generally contrary to what we have observed in red wines, and the reasons for these differences are not immediately evident, but potentially lies in the differential concentration and modification of phenolic compounds in these two systems. Now, finally, I just want to touch on vitamins. Do they play a role? And I want to touch on this because a lot of these fermentation nutrient additives also have different amounts of vitamins in them. It's not always clear what the complement of vitamins is in those nutrient mixes, but definitely they're advertised as having vitamins in there. Generally, it's known that yeast can synthesize most of their own vitamins, but some conditions can lead to vitamin depletion. As with human vitamin intake, there's little evidence for a direct benefit to yeast performance of vitamin supplementation. And mainly the reason is that except for a few exceptional circumstances, there's sufficient vitamins present in their usual environment of grape juice. However, some conditions, so microbial activity, can critically deplete juice vitamin content. And even though they can produce their own vitamins, a depleted juice can lead to stuck or sluggish fermentations. And a similar effect has been attributed to high SO2 concentrations. High SO2 can really strip juice of its vitamin complement, particularly thiamine. So, and high SO2 concentrations in juice can occur via mis-add during juice preparation, or sometimes it's added at high concentrations to preserve juice during transportation. Under these circumstances, vitamin addition through the use of complex nutrients or specific vitamin preparations, of which there are a few in the market, can be beneficial. So things to watch out for: high sulfur, long distance transport, uncontrolled microbial activity. And I guess that sometimes maybe also extends to cold soaks or extended macerations. So in summary, when and what nutrients should be added, I guess the answer is that it all depends. When it comes to rehydration, I would say that take care of the basics and the yeast will take care of themselves. And what do I mean by the basics? I mean appropriate temperature used, good dispersion of the dried yeast in the liquid, and acclimatization of those rehydrated yeast to the more difficult juice conditions prior to addition to the bulk juice. For nutrient addition during fermentation, to understand your juice, understand the YAN conditions prior to nutrient addition. We're not, even with complex nutrients, you're not really necessarily adding a lot of YAN, like I said, was presented earlier, up to maybe 50 mgs per litre. But a well-prepared fresh juice is unlikely to require any additions, assuming sufficient YAN. As I also said, transport, maceration, cold soaks can modify the original juice nutrient status, either up due to additional extraction of nutrients from the bulk solids, or down because other microbial activity present in the juice during that time has had an opportunity to soak up or use some of the nitrogen or vitamins. Nutrient considerations in general may be less important for high solids ferments, but still something we need to think about. DAP addition not always useful in managing H2S, growth-associated H2S, and probably not particularly useful at managing end of fermentation and H2S. In these types of conditions, probably will have to resort still to copper treatment before the first racking. And finally, oxygen use requires an engineering solution to be implemented, and although potentially useful for stimulating fermentation and definitely beneficial, requires probably some experimentation to be sure that you get what you hope for. So finally, I just want to acknowledge the different people involved in various components of this work: Radko, Angus, Martin, Christian, Maurizio, Paul Henschke and Paul Chambers. And then, thank you all for listening. I'll open that up now.